Dear students, today in this particular lecture we are going to learn about charge conservation, equation of continuity, which is an integral part of charge conservation, as well as we are going to learn about displacement current. So here we start. First of all, let us start with the concept of charge conservation. Charge conservation states that in an isolated system, electric charge is always conserved. What is an isolated system? A system which is isolated from other part of the universe is known as isolated system. In an isolated system, suppose there are many bodies, then the bodies can interchange charge amongst them. But whatever happens, the total charge in an isolated system will remain conserved, even if the bodies among themselves interchange charges, but the total charge remains conserved. For example, in that isolated system, suppose the charge is 10 coulomb, then after 5 minutes, after 10 minutes, or forever, as long as no disturbance is introduced into the system, it will remain as 10 coulomb. Related with charge conservation, we have equation of continuity. Before we move to equation of continuity, we need to study little about some definitions, and these definitions include the concept of current density. To understand current density, let us go to this figure. In this figure, I have shown part of a conductor which is carrying electric current, and there is a cross section whose area is A is also shown, and there is a point P. Through that point P, current flow is I is the current. So at the point P, current density is defined as simply current per unit area, provided the current is flowing perpendicular to the area of cross section. Here the current is perpendicular to the area which we have chosen it to be here. So current density is simply current per unit area at the point of reference. What will be the SI unit of current density? It will be ampere per meter square. What is the symbol? J. J is the symbol for current density. Is it a factor quantity? Because you have current and area in the definition of current density. The answer is yes. Current density is a factor quantity. In fact, current density is J is equal to N EV, where V is the drift velocity of charge carriers. We are not going to that definition right now, but here the direction of current density J will be the direction of the current. So now let us move on to the definition of current density. So current density at any point is defined as the quantity of charge passing per second, which is basically current, through a unit area taken perpendicular to the direction of flow of charge at that point. And I have already mentioned it's a factor quantity. Current density unit is ampere per meter square. Okay, now in the previous diagram, this diagram, we had your area, cross-sectional area, exactly perpendicular to the direction of current. But what if area is not perpendicular to the flow of current? How will you link current and current density in that scenario? So we'll go to this diagram. In this diagram, you will see that this area, which I am showing with blue marking right now, is there, but at this point P, electric current is in this direction of J here, which is perpendicular to this cross section, but this cross sectional area, but this particular cross section here, current is not perpendicular to it. So how will you link then? In this case, what we are going to do is that we take the area factor. So at this point P, for this area, which one I am showing with blue marking, here you try to draw the area factor. This particular area is ds in magnitude, and its area factor we know is normal to it, so this is the corresponding area factor for it, and the current density factor is already drawn here. Angle between them is theta. So current is equal to the dot product of current density factor and the patch area factor. So for this patch area ds, the current and current density is linked by I is equal to J dot ds. Now this integration over the surface will come when you have a big surface and ds represents only a patch area of the surface. In other words, I will be just equal to J dot ds in this type of scenario, that is the diagram which right now I am showing. But for a big surface you have to take this sunset integral also. So this is how we will handle if your current and the area factors are not perpendicular to each other. Next we move on to equation of continuity. So if you want equation of continuity, it is in fact is a manifestation or a statement of law of conservation of charge. So to explore equation of continuity, let us go to this figure first. What does this figure represent? This figure represents a surface S. This is a surface S whose volume is V, arbitrary surface, and one small area is chosen, which I am showing by blue marker here, and this small area, its area factor is ds as shown here, and at this small patch area the current density factor is J, and there is an angle between them. So if you want to find out the current through this entire volume V of this surface S, then the equation which I have already shown you will come into consideration. That is, your current will be surface integral of J dot ds over the entire surface. So current I is equal to J dot ds for this surface, which already I have shown you the drawing. Again, how can you represent current? Current is simply integration of this rho dv and its time derivative. Actually, if rho represents volume density of charge, then total charge is volume integral of rho dv. So if I differentiate volume integral of rho dv with time, then it is actually dq dt, which is your current, and current is here surface integral of j dot ds. So I can do a little more trick, and by doing that trick, what I can do is that I can write current, which is surface integral of j dot ds, equal to negative volume integral of del rho del t dv. Now we'll wonder why d dt has become del t partial derivative here, and you may also think how it has become this negative. Why is the negative sign here? So the negative sign is here because whenever charge flows out of a volume, then there is decrease in charge. That is why this negative sign comes into picture. What about the partial derivative? Why is the partial derivative? The partial derivative arrives because the surface S is fixed and the rate of charge within the volume is mainly due to the time rate of change of rho. No other parameter is changing here, only your rho, charge density, that is charge per unit volume, is changing. That is why instead of d dt we are putting a partial derivative here. Next, what we do is that we try to use something called Gauss's divergence theorem. What is Gauss's divergence theorem? Gauss's divergence theorem states that surface integral of A dot ds is equal to volume integral of divergence of A multiplied by dV. I repeat here, it is divergence of A dV. There is no dot here before dV. So here, if instead of A you can put J here, then you will get surface integral of z dot ds is equal to volume integral of divergence of z dv, and hence here you will see that using Gauss's divergence theorem, surface integral of j dot ds becomes volume integral of div of j dv equals to again negative volume integral of del rho del t dv, which is already there. So now what you do is that you transpose this to this one, this and this to the same side of equation. You will get volume integral of div j plus del rho del t over dv equals to 0. Now the surface or the volume which you choose was any surface. We were not restricted to one particular kind of surface here. We did not do that. So this integral must vanish for any arbitrary volume, any surface and any volume enclosed by it. For this particular integral must be 0. So for this to happen, the integrand, that is this part, must be 0, and that is you will have div j plus del rho del t equals to 0. So this div j plus del rho del t equals to 0, that one is simply known as equation of continuity. In other words, in some books you will see it will be written as del dot j plus del rho del t equals to 0. Some books will write del dot j is equal to minus del rho del t. So this is your equation of continuity, and if there is no volume charge, then the expression will go to del dot j equals to then the equation will go to del rho del dot j equals to 0, and if there is no divergence of j, then simply you will get del rho del t equals to 0. Next we are going to discuss about displacement current. What is displacement current? Displacement current, as the name suggests, it should be rate of change of some displacement quantity changing with time. In fact, it is electric displacement, but we are not going to that. First, let us go with our basics. So it was Maxwell who first tried to put the new concept at that time, uh, which was known as displacement current. Before that, we knew only one thing, that whenever current used to flow through a conductor, it produced a magnetic field. In your class 12, you studied so much of that. You learned the expression for magnetic field due to a straight current carrying conductor. You learned magnetic field due to a solenoid, magnetic field expression due to a toroid. All those conditions, you tried to put a current in a coil or a conductor, and there was production of magnetic field. But Maxwell postulated something else. He told that an interesting thing, that a changing electric field in vacuum or even in a dielectric, that can also produce a magnetic field. It was a revolutionary idea at that time, because people did not think that there was a linkage between electric field and magnetic field by that way. So he told that a changing electric field in vacuum or even in a dielectric could also produce a magnetic field. So this changing electric field can be thought to be equivalent to a current, and that current will last as long as the electric field is changing. When the electric field disappears, then there will be no displacement current. So as long as you have a changing electric field, there is a magnetic field, and the changing electric field can simply call equivalent to a current. Okay, so this is the thing. And these changing electric field can produce same magnetic effect just like an ordinary current. That is, you will get a magnetic field out of it. That is, changing electric field, from there you will get a magnetic field also. So how do the concept of displacement current modify our Ampere's circuital law? Actually, the concept of displacement current in fact arrived from the inconsistency in Ampere's circuital law. What is the inconsistency? For this, again, we need to learn a little about charging of a capacitor. So here in this figure, we have a capacitor which is shown here, and the capacitor is charging through a battery. The longer one is positive terminal and the shorter one is negative terminal of the battery. When we connect this key, some of the electrons start flowing from plate A of the capacitor towards the positive terminal of the battery. Same number of electrons, they move towards the plate B of the capacitor. So as time progresses, more and more electrons are moved from your A plate, and electrons get deposited to B plate, and the capacitor is said to be charged. Initially the current is high, but as long as the capacitor starts charging, more and more electrons are removed from A and deposited in B, and charge increases, that current decreases. This type of current is known as transient current. So during charging, one point is to be noted is that current flows from plate A to the positive terminal, and similarly there is flow from B plate, and the negative terminal of the battery, that is the external leads. Which direction current flows in this capacitor, can you tell? So current actually flows from plus terminal towards this E here and this way, which I am showing by blue marked arrow right now, because our electrons are flowing opposite to it. Anyways, but current is in the external leads only, but there is no current in the region which I am showing right now, that is between the capacitor plates. There is no flow of current. Physical current exists in the external leads only. Next, let us try to understand. We have drawn here one loop. This is the loop. This is the loop. This loop is bounded by two surfaces. One surface is S1, this one, this one is your S1 surface. S1, this loop is bounded by two surfaces. This is S1, and there is another surface, this pot shaped one, that is your S2. So this is the thing. You will note that when you take the same loop, within the same loop we have two surfaces. One is S1 and one is S2. P name is given to the loop. But when you take this loop S1, you will see that this wire cuts through that and goes through it. So it encloses current. But when you take the pot shaped one, the wire comes inside this pot shaped surface S2, but it does not go out. That it does not enclose any current carrying conductor. So these are the difference between the surfaces S1 and S2. Now when we try to apply Ampere's circuit law for the surface S1, you know what is Ampere's circuit law. Ampere's circuit law is line integration of B dot dl is equal to mu 0 times the current enclosed by the surface. So if you go to S1, then line integration of B dot dl will be mu 0 times the current enclosed by this surface, and here the conductor goes and cuts through it, so that is why it will be mu 0 into I. But when we apply same Ampere's circuit law, then for the surface S2, then for the surface S2, this one, you have line integration of P dot dl is equal to mu 0 times 0. Why 0? Because as I told earlier, the current carrying conductor wire comes to this pot shaped surface S2. This one is our S2, but it does not cross through it. It comes, enters, but it does not go out, resulting in 0 value for the current for this surface S2. Now there is an inconsistency. The inconsistency is where you are taking the same loop, which is your P loop, and but you have taken two surfaces. For one surface, right hand side is mu 0 I, for another one it is 0. That cannot be, because then that puts a serious contradiction on Ampere's circuit law. You have the same loop as boundary, but it cannot be different expressions on right hand side for this of different values on right hand side you cannot have for the same loop in simple language. So either your Ampere's circuit law is wrong, or you need some correction here. So here Maxwell came to rescue. he told that the inconsistency can be removed if you regard the changing electric field inside the capacitor during charging to be equivalent to a current, and the current is known as displacement current, because during charging the capacitor there is an electric field, and electric field is always changing with time here. As I told you that the current changes during the charging of capacitor, so the charge accumulates on plates A and B, and as charge accumulates there is a change in the electric field in between the plates A and B, and this changing electric field is equivalent to a current known as displacement current. So with this concept, Maxwell corrected the law, and the rewritten law will be line integration of B dot dl equal to mu 0 into I plus ID. Displacement current has a symbol I, and there is a suffix attached to it just to distinguish it from conducting current. So mu 0 I times ID. So when we apply this equation mu 0 I plus ID, that is the modified Ampere's circuital law, Ampere Maxwell law, you can see here the ID value is 0 for the first surface S1, and you have only I, and for the second surface it is not mu 0 into 0, but in fact it is mu 0 into ID, where I is 0, there is no conduction current. And one can show that displacement current and conduction current, they are having same value, that is the displacement current, its value is same as in the inside the capacitor plates, and it as the conduction current outside the capacitor plate. So how can you get the expression for displacement current? We can have an expression for displacement current also. Remember that electric flux inside the surface S2, ultimately inside the capacitor plates, can be written as electric field and area. Area is the A is the area of the capacitor plates, E is the electric field inside the capacitor plates. This expression comes from class 12, so we are not illustrating here. Electric flux phi equals to E into A. So that phi I can write to be 1 by epsilon 0 q by A into A. This again comes from your Gauss's, this one, Gauss's law. 1 by epsilon 0 times the charge enclosed by the surface, and it is actually again derived from for the capacitor. So for the capacitor plate, the electric field is 1 by epsilon 0 q by A, obtained from Gauss's law, or some other consideration that the value is 1 by epsilon 0 q by A. So A and A get cancelled, and phi equals to q by epsilon naught here. And so when you do continue this, then as I told you that electric flux, in fact the electric field inside the capacitor plate is changing with time, so is the electric flux. So you take differentiation d phi dt, then it will be 1 by epsilon 0 dq dt. So as it is 1 by epsilon 0 dq dt, you will find that here dq dt I can write as displacement current id, and epsilon 0 d phi dt remains to that side. And for simple capacitor system, the displacement current expression turns out to be this: id equals to epsilon 0 d phi dt. Here The expression for displacement current is found for a particular situation, that capacitor plate, but I would like to tell you is that it is more general one. It is true for other situations also. That is, the electric flux changing with time multiplied by epsilon 0 is the expression for displacement current. And the displacement current will also have its own displacement current density also, which we will use during Maxwell equation. And as outside the capacitor we will have id equals to 0, so d phi dt equals to 0 because there you don't have the electric field and the current is I only, and inside the capacitor you have your id equals to epsilon 0 d phi dt. Therefore, modified form of Ampere's circuital law is consistent now. So this is what we wanted to tell you in this particular lecture. So let me remind you what we learned. We learned charge conservation. We learned the definition of current density here. We also learned the equation of continuity and what is its physical significance. That is, it represents expression, mathematical expression of conservation of charge. And we also learned displacement current, how the concept of displacement current came into picture, and how Maxwell corrected Ampere's circuital law. In the next lecture, we will go to introduction to Maxwell equation.